So don't worry about it. So your outlines are done. So, yay for you. I don't know. Hopefully they've been of some help.
Absolutely.
Yeah,
Very much.
Good. I know they're a pain, they're a lot of work, but the only way to get this class is to do a lot of work. Yeah. So, yes.
Do you write the final or is it given to me?
I write the final. Yeah, I write the final. I haven't even thought about the final yet, though. So, yeah. I finished exam 4. I'm starting to think of exam 5 because I'm realizing I better get that written pretty soon, and then I'll start on final after that. So, it'll come. Today, what I want to do is I want to spend the majority, probably 2/3 of the class today on acids and bases, and then we'll spend a little bit of time on redox reactions. We'll see how it pans out exactly, and then we'll take our quiz at the end of the class. But I just want to make sure you have a good grasp on acids and bases. Because of all the material that's left, this is the most important one to get. So redox, I can kind of fudge that a little bit as we need it. Certain areas of that aren't as important as the acids and bases. So let's go back to acids and bases. We're going to make sure that we understand this and that we have a good grasp on this. So last time, and part of the problem is this traffic threw me off last time. So I think my head's a little bit more collected today. So we're just going to go through this a little bit systematically, kind of review a little bit, and go into what you need to know for the exam. So we talked about last time the properties of water. Do I need to go over conjugate acid bases again? Are we okay with that? The hydrogen bits? Yeah, okay, good. All right, so we're going to start with the KW conversation. So here we had talked about water and what's going on in water. Water is amphoteric. It can act as either an acid or a base. So in your glasses of water on your desk, you have water molecules reacting with each other, one of them acting as an acid, the other one acting as a base to form your hydronium and your hydroxide ion. They have found that the concentration of the hydronium ion and hydroxide ion are constant. The relationship between them is constant. It never changes. And they've determined this KW, which is this equilibrium product, the concentration of your hydronium times your concentration of your hydroxide will always equal 1 times 10 to the negative 14. This is our equilibrium expression for water. So what this allows us to do is to determine the hydronium ion concentration or the hydroxide ion concentration of any solution if you're given the other. So we kind of walked through this a little bit last time. Where you can write expressions for solving for those concentrations. So to figure out your hydroxide ion concentration, it's just 1 times 10 to the negative 14th divided by your hydronium ion concentration. Or vice versa, to figure out your hydronium ion concentration, it's 1 times 10 to the negative 14th divided by your hydroxide ion concentration. So if you're given one, you can very easily figure out the other one. Like I said, I highly recommend you get very comfortable with using your calculator on these because you will be using exponent features a lot on these. Any questions on this part? Are we doing okay on this part?
Just when you put it into your calculator, do you usually put the bottom number first and then the top one? Or
No, I do 1 exponent negative 14 divided by my hydronium ion concentration.
Okay.
So like let's say for example that I'm told my hydroxide ion concentration is that, and I want to know my hydronium ion concentration. Solve for it real quick. Let's see if we get the same answers. Just do a spot check. Because I guarantee this is on the quiz. Since I wrote it, and I know. And if you need help, once again, with your calculators, if you didn't have them last time, just let me know. I'm happy to come by and look at how to do it. So your setup is just like this. You just take that 1 times 10 to the negative 14th divided by your hydroxide ion concentration, and you should have gotten that as your answer. How do we do? Did I enter it or not?
I did it differently.
No, I didn't enter it wrong. I'll double check, but.
It's like a big number. Do you put negative? Or?
Yes, they're all negative exponents. Make sure you have negative exponents in there. That will change the answer. This is the right answer because I checked it twice.
Now I'm getting 2.
I'm getting 2, like a bunch of zeros and 2.
2 times 10 to the
Your
negative 9.
calculators are misbehaving.
Yeah, I'm getting 2.
It's rounding up.
Mm-hmm.
Okay. You got that? Yeah. Let's see. I don't know that we can change. Let's see if we can change accuracy.
Yours is great. That means I did all this left over.
Okay, there we go. Okay. Those of you whose calculators are pushing, or that are saying 2, somewhere in there, I know hers is over 5. It says SCI. First, and that's for scientific, I think. If you push that, it should give you it in.
You push it after you get that answer?
Yes, after you get the answer.
Is that a negative 9?
That is a negative 9. Yes, sorry. Yeah, and make sure the scientific thing is highlighted.
Whoa.
You probably did just the negative 6 underneath it. That would have been positive. Try it again. Make sure you get the negative 6 underneath it.
Wow. Negative. You got close to the right. All right. How do you
Right? So you're like, you don't make up.
Yeah, this is that same concept.
Oh yeah, I got it.
So first you would go.
I don't know.
No.
Yeah, I gotta do all this.
Oh, I didn't. On this one, I just put 1. Yeah.
Well, the steps are right. All I gotta do is just divide it differently, and I'll just get the different answer. The concept's there. And it's only on the sodium.
Scanning for blood.
Only on the iron. Is there like one?
When I'll watch that. I'll do it. I do not know on yours how to get started.
Does she have one like this?
No, it's this.
Oh, or nine, nothing.
Yeah, but when the answer, when it gives you the answer in decimal notation, I can't figure out how to go into science.
And hot Cheetos. Whoa, where's this? You don't have one. Oh, wow.
I'll put that later. See if we can figure it out.
Yeah.
Okay.
You're just not getting all this for me. What kind of fire?
Now it's giving you the right answer.
So now it's giving 0.02.
Yeah, 14.
this works. I don't know how to do it, so I'll have to think about that.
Carl's been around now since my brother was no, he's 30. Yeah. He uses his computer. You don't. They do a lot of the work that he does. So what? Because his name starts with the calculator.
Okay, the rest of y'all, this is working, so we're going to go on. Okay, so those of you whose calculators are working, did you get this figured out?
Yeah.
All right. So this works both ways. You can go hydroxide to that or hydronium. You can do either one. This is all you have to do. So it's a pretty simple calculation once we get our calculators figured out. Okay. So we had our KW. This allows us to figure these concentrations out of any solution. The other relationship we looked at was the pH, which is equal to the negative log of the concentration of the H+. So you just plug those numbers into your calculator. Once again, some of you will enter log first. Others will enter log after you get the number entered in. And it's always going to be a positive number. So go ahead and figure out the pH of that solution right there. So remember, H+ is just an abbreviation for H3O+.
Oh,
Yeah, this doesn't actually exist in solution. It actually exists as H3O+, but we write it like this just to make it easier to write. So you just plug that number in there. What did you just say? Huh? This number. So the H3O+, these two things are the exact same thing. Those are the same.
If we write it like that on the test, if we put H3O instead of the H, what do you mark it wrong?
H3O+ is more accurate, so. Okay, so you should come up with 8.735.
Oh, yeah. All right.
How are we doing that one? I'll get the right answer there. I might have to do something for those of you that calculators I can't figure out where you could just put something on your test saying mine's one of those funky calculators and I have to just accept whatever it is that you give me because I don't know that I can figure that out. I'm not a computer programmer. Okay, so we okay on this now?
How would you do the inverse one? Because I'm having a hard time with that on my.
That's the next step.
Okay.
Okay, so one way of determining your hydrogen ion concentration is through the relationship between the OH- and the H3O+. The other way is going through the inverse pH. So say you're in lab, you take the pH of the solution and you want to know what the hydronium ion concentration is, you just work backwards. So the concentration of your H3O+ can also equal 10 raised to the negative pH. So in your calculators, usually you have to put in the pH value first, and then you negate it. Then you would go the 10 to the whatever, or you could do 10 to the and put in the negative pH. Once again, it depends on your calculator. So let's say you have let's say your pH is 5.921. I want to know what the hydronium ion concentration is. So go ahead and solve for that.
What to be wrong?
Would it be? You have to have that 0 at the end.
Yes, it should be 366 because there's 3 decimal places. So the number of decimal places in the pH tell you the number of significant figures. So if there's 3 decimal places, you have 3 sig figs. If there's 4 decimal places, you have 4 sig
because
figs.
it's backwards.
Yeah, when you go
Okay.
from concentration to pH, the number of sig figs is the number of decimal places.
Okay.
Does that also apply to the constant calculations with the water's constant?
1 is a given. We're looking at that as a definition, so we're not looking at sig figs.
Okay.
We're ignoring it.
Alright.
No.
Okay, how do we get on this one? Your calculator will probably show like 1.199499 something like that to the -6. So this is just rounded because of the significant figures.
Well, I don't get the negative exponent. I just get a bunch of numbers, so I just move the decimal, and then I get.
Yeah, you have to convert yourself.
Okay.
Yeah, not all the calculators can get science presentation. They're not all that nice.
Okay.
When I have the same calculator as you, I got mine.
The negative log, just negate it in your head. So just put log of that number and then negate it in your head. Well, I rounded it. For the pH, is that what you're talking about? Okay. Other questions on that? Did we figure this one out?
Yeah.
Okay. All right, so that's for the hydrogen. These are the different relationships when we're looking at the hydrogen ion. There's also, in addition to pH, remember pH is a mathematical function. You're just taking the log of something. You can also have what's called the POH. The POH is just the negative log of the concentration of the hydroxide ion. So you're doing the same exact calculations, you're just looking at the hydroxide ion instead of the hydronium ion concentration. So if you were told that your concentration of your hydroxide is 7.92 times 10 to the -13th, I want you to figure out the POH. So the POH. What is your POH?
POH equals the negative log of OH.
The POH is the negative log of the OH concentration. So it's the same exact thing we just did with hydrogen, except now it's hydroxide. Who said that? Sorry. Yes.
Why isn't it 360?
It's you go off of the number of sig figs here, tell you the number of decimal places over here.
Oh.
Yeah. So it's weird because of that log function. So that log function tells you basically what the exponent is. I don't want to get into the algebra behind it. So
Yeah, but
that's the number of decimal places. Decimal places, yes.
why is I got the same answer, but mine says 1.2101. That's like the decimal is shifted one over to the left.
Oh, does it have it times 10 to the second or 10 to the first?
Yeah, 10 to the
To the
first.
first. That's the same answer.
Do you want us
Okay.
to just move it over like that?
pH is typically given like that. Yeah, it's not usually given scientific notation.
Okay.
Probably we changed the setting to get to the scientific notation for the other things. So now it's going to give you everything in scientific notation.
Okay.
Yeah.
Are you using the e-button when you're doing this?
know how to plug it in, but what formula?
Okay, other questions on this one?
It's not really on the calculations, but why is it that the OH scale is flipped? That's kind of what I understood from the reading, that it's
They're
bases are
related.
added.
Yeah, the bases. Because as you increase hydroxide ion concentration, you decrease hydronium ion concentration. Because remember, they're always, those two concentrations times each other are always equals 1 times 10 to the negative 14. So if you increase one, you have to decrease the other.
Right, like, that makes sense, but when you, so if you say, okay, on the OH scale, it's from, 8 to 14 is acid, pretty much?
Oh, like yeah, because the pH is, you're taking the opposite function. So like when you get a really high POH, like that 12.101, that means you have an acid because your OH concentration is very low. So I don't usually make you identify some things an acid or a base based off the pOH scale. We go off the pH scale because no one uses the pOH scale, realistically. So we just talk about pH. Like I've never seen a full test strip that tests for pOH. So yeah.
Yeah.
Okay. Other questions on this one? All right. Likewise with this, you can go vice versa. If you want to figure out your OH concentration, it's just 10 to the negative pOH. So it's the same idea here. You just do the inverse function again. So let's say that I have a pOH. And let's see. My pOH is that. What would my OH concentration be? That's a 4. That's a 4, sorry. Error.
That makes sense.
Okay, how do you
Now
on
you're
that
not
one?
panicking, huh?
I know.
Any questions on that one?
No, it looks good.
I'm trying to figure out why there's 3 decimal places because there's 6.
There's 466 here based off of the 4 decimal places here.
Okay, I'm getting when it's
Yeah, that's going to take some practice in your head. I know. It's so different than what we've done. Okay, questions on the mechanics behind this? Everyone's figured out their calculators? Good. Do we feel better about these?
Yeah.
Okay. So here I have kind of the relationships of H, the different ways of calculating the concentrations of them. There's one other relationship that we have, and that is that the pH plus the pOH is going to equal 14. So that relationship always holds true. It's related to that KW. So this is all related together mathematically speaking. We're not going to derive it, but it's all related.
The KW is the first one.
All right, so what this allows you to do, if you look at that chart that I gave you, this allows us to be able to complete this chart. If you know one of these things, you can figure out all of the rest of them.
Mm-hmm.
And there are multiple ways that you can figure these out depending on what you would like to do. So let's look at our first one. We have our hydronium ion concentration is 5.48 times 10 to the negative 7. We want to know the rest of these. Now, I can do this multiple ways. If I know my hydronium ion concentration, can I figure out my hydroxide ion concentration?
Yeah.
Yes, because I have that relationship over there on the far right, the top right. If I know my hydronium ion concentration, I can figure out my pH. Just use this right here. If I know my hydroxide ion concentration, because I just calculated it, I can figure out my pOH. Or, since I know my pH, I can use this to figure out my pOH. Or, I can go from here, figure out my pH, then figure out my pOH, and go backwards to figure out my OH. It doesn't matter how you do it, just as long as it gets done. So there's multiple ways of doing it. There's no right or wrong answer here. I should say there's no right or wrong method. There are right or wrong answers, not methods. Okay, so if you didn't get this first one done, go ahead and try this real fast, doing whichever way you want to do, and we'll go over them in just a minute.
Okay.
We don't consider something neutral unless it's exactly
It's
7.
exactly 7. Yes.
What about those of us who have like the exponents coming up the same?
As long like what did you get? Did you get 2 times 10 to the negative 8 for the OH?
For the OH negative, 1.2 times 10 to the negative.
There's something wrong that you're entering into your calculator then. Because when I was doing yours, I got the exponents right, but it was the numbers that were wrong. That sounds like you're not dividing by a negative exponent. You're dividing by a positive exponent. Okay, how do we do on this one? Any other questions on this one? You guys get this?
Need to practice sig figs.
It's the sig figs will take practice.
Oh,
So there's 3 sig figs here, so there has to be 3 decimal places here. Now, is this an acid or a base or neutral?
It's a base, acid.
This is an acid. So acids, if the pH is less than 7, you have an acid. If it's equal to 7, you have neutral. And if it is greater than 7, you have a base. So I do ask you to identify if it's acid, base, or neutral. So make sure you have that as your guideline there. Okay, so we good on this one? Let's look at the next one then. Go ahead and fill out that chart real quick if you haven't gotten to it. I'll scribble up the answers here so you can check them as you're going through.
The rule of sig figs is only for pH or POH, right?
Yeah, this is when you're going pH, POH to the constant back and forth, yeah.
I don't know why it won't. Right.
last one for the hydronium
Mm-hmm.
concentration, I got the same thing, but I got a 5 out of it. There's 5, 6, 6 that you're given.
Start off with what this side concentration right here.
Yeah.
So you have 5 total. This one has 5 total.
So you're not going after the decimal places on that one?
If I know my hydroxide ion concentration, I have 5, 6, 6. I'm doing division, so that goes off the same number, 6, 6. If decimal places goes to when I do pH and pOH. Yeah. One is negative 4. 1 exponent. Yeah, don't do
So like something like this where you hold on.
Oh, wow. Here's your decimal places would be 4.
Yeah. Oh, no, not for the HBO. For the HBO, yeah, you go based on. Yeah. Yeah. That would be the same. But the news one. No.
Yeah, because you go off that. Oh no, the total number of videos. So it would be 5. So we have
We have to be 5 decimal places because it's 5, 6, 8. Yeah.
no, but I like their They're not bad, but yeah.
I can see afterwards to figure it out. I've never been stumped by a calculator in years, so it's just stuff. Okay, how do we do on this?
Getting better.
Getting better. Okay.
It's just a 6 bit.
Yeah. For this one right here, is this an acid or a base?
Oh, that's acid.
Acid. How about the next one? Is this an acid or a base? Base. Base. And then our last one, is that an acid or a base?
Base.
Base. Okay. We have to move on. So, yes.
What am I looking at?
The pH. Yeah, I'll go off the pH. That'll be your easiest way to do it. Okay, other questions on this one? All right, let's go on to titration, and then we will start chapter 16. So we're going to skip buffers, so just ignore that section. Time constraints dictate otherwise. Acid-based titration, you have done these calculations before, you just didn't realize it. This is just stoichiometry. For acid-based titration, there's a different method of approaching these calculations that we can use. If you want to do it the way that, if you like to figure out how to do it using stoichiometry, that's fine. I'm not going to go over that. I'm going to go over this other method here. So I give you basically a titration. If you look at a titration, which we're doing in lab today, you're taking an acid or a base of unknown concentration, and you're adding a known amount of a known concentration to it, and you can figure out, based on that information, what the concentration is of that other acid or base. So we use an indicator, and in the lab we'll use something called phenolphthalein, and it turns pink when you reach what's called the endpoint. The endpoint is approximately where the concentration of the acid and the concentration of the base is equal. So you have the same number of moles of each one in the solution. So I give you the strategy right there of how to actually approach these equations, the 4-step strategy. So when we look at the problem, we're going to walk through the problems using this strategy. We have our first one says it takes 25 mils of a 0.05 molar hydrochloric acid solution to neutralize 345 mils of a sodium hydroxide solution. We want to know what is the concentration of the NaOH solution. So according to my strategy, what is my first step?
Write your balance equation.
Write my balanced equation. So my balanced equation, I have hydrochloric acid plus sodium hydroxide. Those are given to me. My products you have to figure out. An acid plus a base will always yield a salt plus water. So what is my salt going to be here? NaCl, sodium chloride. So I have sodium chloride plus
H2O.
water. So that is my balanced equation right there. What is my second step? It's already balanced. Well, I didn't really stop. It's balanced.
Yeah, it's balanced.
Yeah. So what is the second thing I do now?
Determine the moles of
I determine the moles of the titrant. So the titrant is the thing that you've added to the solution. So it's what I have. We'll talk about urets in lab this week. It's what I have in my glassware that I'm adding to my unknown. So in this case, my moles of my titrant and HCl is my titrant. So my second step is to determine the number of moles. If I have my volume and I have my molarity, can I figure out the number of moles?
Mm-hmm.
Yeah, because molarity is your moles per liter, right? So in this case, we have our molarity is 0.05 moles per liter. And I'm told that I have 25 mils of solution, so make sure to convert those units to liters. So I can figure out that I have 1.25 times 10 to the negative third moles of HCl. Now with this one, how many sig figs should I have in that final answer? One. So I'm going to just keep track of this because I want to have those 3 sig figs for the rest of my calculations. So I'm just going to kind of keep track of that. That's where my sig figs should end. My next step, step 3, is that I need to determine the moles of my unknown. How do I determine the moles of my unknown? If I know moles of HCl, can I figure out moles of NaOH? Yeah, my mole to mole ratio, right? So using our stoichiometry. So we know that we have 1.25 times 10 to the negative third moles of HCl. And according to my balanced reaction, for every 1 mole of HCl, there's 1 mole of sodium hydroxide. And once again, keep in mind that we should only have 1 sig fig in that final answer. Questions on how I got to that point? So this is stoichiometry coming up to bite you if you don't remember how to do it. Okay, the next thing, the last step, the fourth thing that we do, is to actually determine the concentration now of our sodium hydroxide. I have my number of moles right here. Where do I get my volume from? Read your problem. It's in the problem, right?
345 milliliters.
So I have my moles. I have my volume. Can I figure out molarity?
Yeah.
Yeah, it's just moles per liter, right? So I have my moles is 1.25 times 10 to the negative third. And my volume for this one was 345 milliliters. Remember, convert it back into liters. So when you do this, you take that and divide it, you end up with 3.6 times 10 to the negative third molar. But remember, we only have one sig fig up here on the top, so I had to round it to 4 times 10 to the negative third molar of sodium hydroxide. So using titration, I was able to figure out the concentration of my sodium hydroxide solution. And we got this perfect now, right? I'm tired. All right, let's look at the second problem. Okay, so my second problem, we're titrating a sulfuric acid solution with potassium hydroxide, and we want to know, we're trying to figure out the concentration of the sulfuric acid solution. So my first step is to do what?
Write your value.
Write my balanced equation. So if I have potassium hydroxide and I'm adding it to sulfuric acid, what is my salt going to be?
K2SO4.
Potassium sulfate, right? So I have K2SO4. And then I have water over here. Make sure you balance this.
I have a question.
Yes.
We're writing this out on the test suite.
No, not for this. Yeah, no. This isn't ionic and so all that stuff, so you don't have to worry about that for that. If you want to, that's fine, but that's just more work. I like to make things easier on myself. So. Okay, so this is our balanced equation. Then our next step is to do what? The moles of the titrant, right? So in this case, we're told the volume and molarity of the potassium hydroxide, so that's our titrant. So we have our molarity is 0.5 molar, so that's just 0.5 moles per liter. Convert your volume into liters. Okay, and that tells you how many moles of potassium hydroxide you have. Once again, this will be a one significant figure problem. So make sure you keep track of that as you're going through it. Once I have my moles of potassium hydroxide, what do I do?
Yeah, mole ratio.
My mole-to-mole ratio between potassium hydroxide and sulfuric acid, right? So I need to figure out my moles of sulfuric acid. So I have 0.025 moles of potassium hydroxide. Now for this one, I know I have 2 moles of potassium hydroxide for every 1 mole of sulfuric acid. So I know that I have 0.125 moles of sulfuric acid. Now that I know the moles of sulfuric acid, can I get to my molarity of sulfuric acid? Bless you. How do I get to the molarity? I just divide that by the volume, right? So I'm going to take that. And once again, remember to convert that volume into liters. So you do that, and you end up being told that you have 0.1 molar H2SO4, and it should only have 1 sig fig, so that's actually the correct answer there. Okay, questions on titration?
Let's get the 0.5.
Right here? Yeah. This comes from the concentration, because I'm told that I have 0.5 molar potassium hydroxide. Remember, this is the same thing as that. I just rewrote it moles per liter. So that big M is the same as moles over liter. It's the same thing.
Okay.
So I just rewrote it that way.
And then under the 0.05 liters, that's just 1 mole, right?
No, there's nothing under that. It's just, that's our volume. Sorry. There's doesn't give me a line there.
Oh.
Yeah, that's not over anything. Sorry about that.
I have a question.
Yes.
You have it as 0.1, isn't it just 1?
Yeah, that is 1.
Okay.
Oh no, I'm missing a 0 in here.
Yeah.
Sorry, I'm missing a 0. I copied it without a 0. I apologize. I missed that when I was looking at it. Time for glasses. Not really. Okay, other questions on that? All right, this is, you're going to be doing titrations in lab today, so you'll get more practice on this in lab. But now we're going to go on to chapter 16, so we'll get through hopefully the first couple pages and then we'll finish. We'll do the half reactions on Thursday. I'm not going to start those today.
We're starting with activity theories, or?
No, the determining oxidation numbers is what the first topic is, oxidation states.
Oh.
So we'll just do oxidation states and we'll do half reactions and activity series, all that stuff next time. You guys are hoping I'll leave this up for the period of time.
Yeah.
Oh, on the quiz with intermolecular forces, is that something like, I don't know, and to draw the Lewis dot structure and determine?
It's just identify the intermolecular force.
Okay.
Okay. Do we feel better about acids and bases now?
Yes.
Okay. Hopefully. Some of you guys are still hiding your eyes from me. I love that. I can still see you. Okay. So oxidation and reduction is chapter 16. This is on the next exam. So chapter 14 is the end for the exam 4. This is now going on to exam 5. All right. So we talked about oxidation reduction reactions very briefly back in like chapter 5 or 6, something like that. So let's kind of go through and review what these terms mean. Oxidation. What is oxidation?
Gain of oxygen, loss of electron.
Or
Gain of oxygen or loss of an electron.
hydrogen.
Or loss of a hydrogen. Yeah. Okay, what is reduction?
Loss of oxygen, gain of
Or hydrogen.
Or hydrogen, yeah. So there's multiple definitions. Like I said here, it says that there's more than one definition, so you can have multiple ones. So my favorite term for oxidation or reduction, I kind of just ignore the oxygen, hydrogen thing, because if you just look at the electrons, that tells you everything you need to know. So if it gains electrons, it's going to be reduced. If it's losing electrons, it's going to be oxidized. That's oxidation. When we talk about oxidizing agent, what is an oxidizing agent? It causes the reduction. So your oxidizing agent is actually the thing that becomes reduced. So your oxidizing agent goes from having a more positive charge to having a more negative charge. It's weird. Reducing agents are actually oxidized. So those terms kind of go back and forth there. So reducing agents, they end up becoming oxidized, they end up becoming more positive. All right, an oxidation number. What is an oxidation number? Something we've used many times in this class, you just didn't know what it was called. What's an oxidation number?
It's a number that is computed for each element based on the number of electrons assigned.
Okay, so you calculate it for each element. We've learned it as something else. Any ideas what I've called an oxidation number up to this point? A what?
It's not the charge.
It's not the electron, it's the what?
It's not the charge, right?
It is a charge.
Oh, it is.
Yeah.
Yeah, we called it charge. So oxidation numbers and charges are basically the same thing. So they just have this fancy term. So like if I write up here, FeCl3, what is FeCl3 called?
Iron chloride?
Iron 3 chloride.
Iron 3 chloride. So if I ask you what the charge of iron is here, what is it?
3 plus?
3 plus. So we've said that's the charge. It's also the oxidation number. They're the same thing. So those go hand in hand. Now Now, your textbook gives you some rules for assigning oxidation numbers, and sometimes this becomes important because there can be times where we have conflicting information. So the rules on page 581, and I don't have that with me. What is the first thing?
3 elements have 0 oxidation state.
3 elements are 0. So, for example, by 3 elements, they're talking about you see Cu like that by itself, oxidation number 0. Let's say you see I2, oxidation number is 0. Those are 3 elements by themselves. Those are examples of those. So that's rule number 1. What's rule number 2?
Oxidation state is equal to the charge.
Okay, so this is what we were just talking about, like with the iron 3 chloride, that the oxidation number of iron is equal to 3 plus because the charge is 3 plus. Same exact thing. And you are giving me these in order, right?
Yes.
It doesn't matter. Okay.
Is it always the charge of the first element?
This will be where the rest of the rules will help us in a second.
Okay.
Yeah. What's the third rule?
The sum of the oxidation state should equal 0 if it's a free element, or if it's an ion, it should equal the charge.
Okay, so what this means is, like, if I look at the iron 3 chloride again, iron has a charge of 3 plus. What is the charge of chlorine?
1 minus.
1 minus, but how many of those do I have?
3.
3. So I have 3 times 1 minus. When I add those up, that equals 0. So they add up to 0. It's just like when we were talking about making compounds and formulas. So exact same thing. If it's an ion, let's say it's PO4 3 minus. So we're talking about, what is that polyatomic ion?
Phosphate.
Phosphate. So this is an ion. The sums of these charges have to add up to be 3 minus. The oxidation number for oxygen doesn't really change. It's usually 2 minus. So based on that, if I know oxygen's 2 minus, how many oxygens do I have there?
4.
4. So what's 4 times negative 2?
Negative 8.
Negative 8. My oxidation number for phosphorus plus this has to equal a negative 3. So what plus this equals negative 3? 5, right? So that tells me that my phosphorus is going to be 5 plus. So that's what that's talking about.
Yeah, because that's how I did all the other ones, but that doesn't apply to every. Wait, never mind. I'll just wait until you do that.
Okay.
Only if it's an ion.
All right, what's the next rule?
In compounds, group 1 has a +1 oxidation state, and group 2 has a 2 plus oxidation state.
And the next one?
And then it just gives you some, like, chlorine is -1, hydrogen is +1, oxygen is
Do them in order.
-2. Oh.
Is it all one rule?
For
Yeah.
number 5? I got.
And then it says group 7A is -1, 6A is -2, 5A is -2.
Okay, did I miss anything there?
The oxygen is -2 and hydrogen is +1.
Which comes first, the oxygen or the hydrogen?
I have
Hydrogen.
Hydrogen, I thought. Okay.
Sorry, I wrote it all crazy.
It does matter. Okay. The way these rules work, the one that's on the top takes precedence over the one that's on the bottom. So most of these, very straightforward.
Yeah.
The 1A and 2A, can these have multiple charges?
No.
If we look at group 1A and 2A, can those metals have multiple charges?
No.
No. Hence, their oxidation numbers never change. So unless you have a free element, if you have sodium by itself, it's 0. But when it's sodium in a compound, it's always 1 plus. Magnesium in a compound, always 2 plus. Those never change. When you get down to the nonmetals, the nonmetals have different charges when they're in an ionic compound.
Yeah.
Nonmetals.
No.
No. We're not talking transition metals. We're talking nonmetals. This is why these charges are always consistent. They don't change. The only exception to that would be oxygen here. Notice hydrogen, it comes over here. The reason being, oxygen forms a polyatomic ion all by itself. Remember that O2 2 minus thing? That was peroxide, way back from then. That has a different oxidation number than our 2 negative. So if we look at water versus peroxide, here, hydrogen goes first. So hydrogen, we go off the first. It's 1 plus. We have two things that are positive. So what does the oxidation number of oxygen have to be here? There's only one of them.
Negative.
2 negative, right? So that gives us our 0. Looking down here at peroxide, if I look now, hydrogen once again comes first. So I know that it's 2 times 1 plus. Now how many oxygens do I have?
2.
2. So what is the charge of my oxygen going to be?
1 minus.
1 minus. So I have to have 2 times that 1 negative equals 0. So here, my oxidation number is equal to a 1 negative. So it can change. That's why the hydrogen came first. So it's whatever rule is on top takes precedence. It comes first. So let's look at some of those problems then. Okay, good. Yeah, I'm going to try to just get through these. If I can find them. All right, so let's identify some oxidation numbers to these things. Okay, so in this case, we have molybdenum, which is a transition metal, oxidation state unknown. What do you think would be the place to start on this when assigning oxidation numbers? Oxygen. What is oxygen's number going to be?
2 minus.
2 minus. So oxygen is 2 minus. How many of those do I have?
4.
4. So I have a total of 8 negatives, but what do these have to add up to be?
Negative 2.
2 negative, because I have a charge. So my oxygen oxidation numbers plus my molybdenum have to equal negative 2. What is MO going to be? 6. So we're back to basic algebra. Questions on that one? Yes.
4, negative 2, negative 2 is 4.
This is that subscript from there, and the negative 2 is the charge of oxygen. And this is the ion's charge, which goes down here. Yeah. Sorry, that's a little confusing. I can see that.
No, that's fine.
Okay, the next one. For this one, where am I going to start?
Wherever you'd like.
My oxygen again. What's the charge of oxygen? 2 negative, so I have 3 times that 2 negative. And then my ion charge is 2 negative. So sulfur plus that has to equal 2 negative, so what's sulfur going to be? 4 positive.
Would it be wrong if you started with sulfur? I didn't, but I'm just
No,
wondering.
you should start with oxygen, because oxygen is a given down here. Sulfur is not. Okay, the next one. Where are we starting? Oxygen again. So for this one, we have 4 oxygens times a 2 minus charge has to add up to be 3 minus. So what is the charge of arsenic going to be? 5. And then the next one down there is that. Where do you start with this one?
I did sulfur, but I
Sulfur.
used 2 minus.
Yeah, we start with sulfur because we don't know the arsenic. The arsenic one can change. So sulfur is 2 minus. So we have 3 times 2 minus. And what do these have to add up to equal?
0.
0 plus our arsenic. So what is, we need a total of 6 positives, right? But how many arsenics do I have? 2. So what's that charge going to be? 3. So my oxidation number will be 3 positives. So it really is just like writing formulas from names. That same concept. Having to figure out their charges. Okay, questions on that? We'll go over the rest of that on Thursday. I can book it through PowerPoint. A lot easier than this. All right, I will put the PowerPoints on Blackboard for y'all too, so you can actually download those. So those will be available for you. Chapter 18 I have made. I do not have chapter 19 made yet. Go ahead and clear everything off.